I've decided to use aluminum for the gears in this gearbox because it's light and because it's strong. And I managed to purchase a relatively large chunk of aluminum at one of the local material suppliers. This particular piece is 5 inches wide, and it's stamped with the specification for the material on one side of it. You can see right here it says it's 6061 T6 511, which is the 6061 aluminum alloy that we're going to use for these gears. This piece is 3/8 of an inch thick, so it needs to be milled down flat to 1/4 of an inch, which I will chop a chunk of it off and then mill it down. Oh, we're working on the gearbox again, and now we're making the center holes for the gearbox. The idea with these gearbox is to cut them all together, and so I'm going to make all the blanks identical and then stack them on an arbor. We're getting there. So we have the center holes for the gear arbor done, and the last thing to do now is to cut the outer contour of the gear blanks, and then we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 gears. And that's a lot more than we're going to need for this job. Okay, we're cutting the gear blanks today to make the gears. You know, so I've taken those gear blanks that we cut and I've stacked them on an arbor that I made up out of a piece of threaded rod, which is 1/2 inch, and they have 1/2 inch holes in them, so it works out pretty good. This allows me to tighten them together pretty thoroughly with these nuts here. We're going to cut these gears on the milling machine using a gear cutter. I don't know how hard it is to see that gear cutter. This is it right here. It's a rotary gear cutter. It's a diametral pitch of 16. And it can cut gear teeth anywhere from 21 to 25 teeth. In this case, the gear has 24 teeth. So I'm going to go ahead and begin. I've already cut a few of the teeth. So we'll start the cycle again. First thing I have to do is set the correct rotational spacing on the 4th axis. So I'll do that with a command to rotate the 4th axis to 120 degrees, which is the next gear that we're going to cut. Fourth axis rotates to the right location. Now we'll go ahead and cut this gear. This is the rough cut, and the rough cut's 131 thousandths. It will be followed by a 10 thousandths final cut for a total working depth of each tooth of 141 thousandths. And incidentally, the total working depth for any of these teeth, that is, any of these gears, to determine the working depth can be determined from a variety of charts that are located in books such as Machinery's Handbook. Now we'll get that second pass. We're taking only 10 thousandths. Always want to take a final pass, because an initial pass that takes a large cut can cause the whole work to flex, and that reduces the accuracy of the cut. So you can rough by taking a heavy cut, but then you have to come back with a very light cut on the final in order to ensure the final accuracy of the cut. So that tooth is now nearly complete. The system is set to restore to 0, so 135. The next one is going to be 150, so we'll go to G0, A150, and rotate around for the next cut. And this is the way it will go until all the teeth are cut. Okay, I'm not going to bore you to death watching this machine work. We'll come back when we have all the rest of the gears cut. Alright, the gear teeth have been cut, and they're looking pretty good. The next thing I have to do is take it apart, and then we'll inspect each of these gears and see what they look like. It turns out that I was not satisfied with that first set of gears. I do believe that the gear blanks rotated a little bit on my makeshift threaded rod arbor. So I cut them again in very much the same way, except this time I made a different kind of arbor onto which I pressed the gears. And they turned out to be excellent on the second pass through. Well, today I'm going to start on the housing body. This is going to be a solid piece. I have a drawing of it here that hopefully we can get focused on. And it shows that it's 3.74 inches in its largest dimension. I'm going to make this out of a chunk of aluminum billet that I picked up at a material wholesaler. A little bit less expensive to buy material, that way you end up buying a little bit more of it, but you pay for it basically by the pound. I cut this piece of material on a saw. Now I'm going to go ahead and machine it out. I have it mounted to an aluminum base plate in the vise here, and I've mounted it with these 3 screws, and I am hoping that that is going to be adequate to secure this thing positively so it doesn't wobble around, because the tolerances on it are fairly close. So we're going to go ahead and get started here. I've made a little bit of a test cut on top, and I've aligned the vise and trammed it in, and we're going to go ahead and try and cut this thing out. It will probably take a little bit of time, so I'll just show excerpts of it. that's not so good. What happened is that the tool touched the hardened steel back of the vise here because I had not anticipated that I didn't leave enough clearance in here for it. Apparently I left enough clearance for the tool, but the NC program apparently decided to take some more room than that. So when the tool hit the hardened steel, it buggered the tool up, and that stopped it from cutting properly. So we'll clean this mess up and see what we can do to recover from it. Well, here's the story on the tool. See, the tool now has aluminum welded to it here. That actually happened a little bit after the tool contacted the hardened steel, because right there is where the tool actually hit the tool steel of the jaw, and that ruined the tool. And after the tool was ruined, it stopped cutting properly, and then it immediately built up a layer of aluminum that adhered to the tool itself. Here we go. It looks pretty good, and you can see that high-speed steel tool with coolant actually produces a pretty good surface finish on aluminum. Here's where the problem was. This is where the tool hit the vise. It hit the vise right there. There's a little nick in the back of the vise, and then this is where it started cutting and lost its ability to cut. So we're going to have to make this cut again with a different tool, and I'm going to have to do something about the positioning of the tool in the vise. Unfortunately, the plate is right up against the fixed jaw, so I'm going to have to allow more space in there for that tool to work in this area here. It's one of the hazards of CNC machining is that the tool paths sometimes, if you don't model the fixtures and the vise, which I didn't, you can't always predict collisions, and that's what we had here, was a little collision. Here, this is the tool. It's a 1/2-inch high-speed steel, and it just touched right on the edge here, and it was enough to take the edge off of the cutting edge off the tool. I got another one here. I bought 2 of these, and you can see the difference in the edges between the damaged one and the undamaged one. It's actually taken a little chip right out of it right there, and that just, it's on the most critical part of the tool, right at the face where it cuts, and it just ruined the cutting ability of the tool. Otherwise, I like the tool though. All right, well, I appear to have fixed my screw up, and you can see now that I went ahead and re-indexed and re-indicated the part with the new tool in place, and allowing for the additional space in the back. I was able to recut that same area again. Again, one of the other things that's cool about CNC is that you can do that as long as you can index, that is, indicate the part accurately enough. You can go right back to where you were and pick up where you left off. And the next part of this process is I'm going to go ahead and remove the part, and then I'm going to have to flip it upside down and re-secure it to the mounting plate. It is symmetrical about that y-axis center line there, so that I should be able to recover and machine the other side of it just so it looks just exactly like this side of it does. Time will tell. I completed the housing off camera, and it looks pretty good, although you can tell that it was flipped upside down. There's a little mark all around the periphery where the two sides were joined. I also completed and installed the outer shaft bearing holder, which provides the main thrust support for the bearing holding the outer shaft. And that is attached to the housing with screws, as you can see. I also completed the shaft for the first idler, which contains 2 gears, if you recall. I made the shaft out of aluminum, and because I have to contain slippage between the shaft and the gears, I had to install woodruff keys. The woodruff keys were installed by cutting a woodruff key slot on the milling machine, as you can see here, and then pushing the keys into the key slots and pressing the gears over the top. Next time I'm going to work on the second idler, which I intend to make the shaft and the gear out of one single piece. Hope you join me.